Okay, let me just switch my modes here, get my discrete stuff ready. All right, we've been talking about writing proofs and stuff, and we're going to continue with that, and then talk about mathematical induction, which is another type of another technique for writing a proof. And that should probably fill out today's class. We're turning in assignment 3 today. Does anybody have questions? Actually, let me address one that I didn't get a chance to answer via email because I was teaching another class. I got an email asking about, I think it was the first question, where they give us a function, and then they say, figure it out if it's injective, and if it is, prove it, and if it's not, find a counterexample. And I got an email saying, I know it's injective, but I just can't figure out a way to prove it because the absolute values are tricky. So I guess what I would say to that is, like, what have we done to kind of get a sense for what this function does? We look at the formula, right? But like, let's get a feel for it. I mean, it's defined, I think, on all reals, but we could start just by plugging in some numbers, and for convenience, I like whole numbers. We might throw some rationals or irrationals in. Oh, whoops. Sorry. Absolute value, not floor function. So that gives us 2, f of 3. And that gives us 6. What does it do to the output, essentially?
Doubles it.
Yeah. Does it do that to all outputs?
No, negative will cancel them out into 0.
Right, like,
So
so f of negative 1, what do we get there?
0.
Mm-hmm. Let's plug in another negative. What do we get?
0 again.
Mm-hmm. So let's think about these particular, I mean, you could find other numbers too, whatever. Like, there's nothing special about these exact ones that I picked, but we could look at these particular ones. And what do we think about how we would go about showing it's injective?
It's not injective.
Well, yeah, why?
Because the negative number doesn't map to the real number.
Well, it does map to a real number. It doesn't.
It doesn't map to a positive.
Yeah, and it's okay if it doesn't map to a positive. It's not that we need it to map to a particular number. But you pointed out in particular the negatives, right?
Oh, because f of b minus 1 and f of minus 3 both equal 0.
Uh-huh.
So it can't be injective.
Yeah, right? If it's injective, then different inputs have to map to different outputs. But here we have 2 different values that map to the same out, right? We doubled up on outs. So by definition, it can't be injective. So if you're struggling with the algebra for how to show it's injective, I have good news for you. You can't show it's injective. Questions before we get to one of the more fun proofs that we're going to write today. Actually, all the proofs are pretty fun. We're going to prove, you guys, are you ready for this? We're going to prove, like, I don't want to spoil, like, I feel like I'm going to spoil the surprise.
That's all right.
But we're going to prove that that there's no integers between 0 and 1, which just feels like, how do you prove something that feels obvious? We're going to find out. That's pretty great. Okay, well, I can see you're all pretty excited, so let's just get down to business. All right, we're going to do a contradiction proof. Contradiction proofs are pretty fun. The idea behind a contradiction proof is you say, let's suppose, we want to prove, in this case, prove that square root of 2 is an irrational. With a contradiction proof, you start out supposing that this isn't the case, and then you show that if that weren't the case, if what we're trying to show, if it weren't true, like the sky would come falling down around us where we are, and since that's not happening, there must be something wrong with our assumption in the first place. So first, here's a little just background, just this will be important. A rational number the key word, the root word in rational is ratio. So a rational number is one that can be written as a ratio of integers in lowest terms, and that's an important part. In other words, can be written as a reduced fraction. So what makes a fraction reduced? Like we know that 3/12 is not reduced, but 1/4 is. What makes 3/12 not reduced?
It's as low as you can go. Like 1/4 is the lowest you can go.
Right, but why is 3/12 not?
Because both those numbers are ruled by a similar number, the same number.
Yeah, right. The top and the bottom have a common divisor. Okay. So if something is reduced, that means that the numerator and denominator have no common divisors. Great. So an irrational number is just not rational. So that's just a little background that we need. And then we're pretty much ready to go. So we're going to prove by contradiction that the square root of 2 is irrational. If we're proving by contradiction, we're going to start out by supposing that it is rational. Let's suppose, for contradiction, sorry. So I just want to point out that when I begin this, when we start a proof by contradiction, we suppose that whatever we're trying to show isn't the case. But I'm also letting the reader know where I'm going. Let's suppose for contradiction, now the reader knows what to expect. What do we get when we say that the square root of 2 is rational? We get exactly what we said a rational number was. We can write it as a reduced fraction, right? So I can write it as some fraction where the top and the bottom don't have any common divisors. So let's say the square root of 2 is equal to a over b, where a and b have no common divisors. Now let's see what we can do with this. here we have an equation. I'm going to start out, I'm going to get rid of that radical. We could square both sides. So this means that 2 is a squared over b squared. Now I like that there's no radical, but I kind of just don't want to work with fractions right now. I'd rather work with integers. So I'm going to multiply both sides by b squared. So a squared is 2 times b squared. A and b are integers. We know that. And a squared is 2 times b squared. What is this? Look at this equation that we've just written. What does that tell us about a squared? Really?
Twice as big as b squared.
Okay. Let's focus on the twice part. What kind of number is a squared? We've written it as 2 times something. No, probably not. I mean, it's not an exponential number, but if we ignore the fact that it could be 2 times anything, like it happens to be 2 times b squared, right? B is an integer. B squared is an integer, and we've written a squared as 2 times some integer. We did stuff with this last class. In fact, the last 2 examples.
That means squared is divided by 2, right? So
Say that again.
conclusion here, since a squared is equal to something, that means 2 divides it.
2 divides it. Yeah, in other words, a squared is even, right?
Yeah.
I was just about to say that.
Now, if a squared is even, look back on what we did last class. What does that mean? What does that tell us about a?
An odd number times an odd number is an odd number, so we have to conclude that a is even.
Yeah, I mean, we showed that in example 2.2 that if n squared is even, then n is even. So if a squared is even, we know a is even. Awesome. We are making progress. A is even, and we know if something's even, then we can write it as 2 times an integer. So let's do that. Now, up here, we had this 2b squared equals a squared. I'm going to just label that with a little star. So we're going to go back to that equation, and we're going to use the fact that a is 2 times some integer k, and we're going to substitute that. So we start with the equation 2b squared equals a squared. Make the substitution so it looks like 2b squared equals 2k, all squared. We'll do a little algebra. 2k times 2k is 4k squared. to cancel out a common factor of 2, we get b squared equals 2k squared. What does that mean about b? Or b squared, rather. Let's do that one first. Mm-hmm. And so what do we know about b?
Also,
Yeah. Okay. Now we're almost done. Up here, we were able to deduce that a is even. And down here now we just barely deduce that b is even. What does that mean if they're both even?
They're not reduced.
Yeah, the fraction can't be reduced. A and b have a common factor. So this contradicts our assumption that we could write the square root of 2 as a reduced fraction. So there must be something wrong with our assumption. And the square root of 2 is irrational. How's that? This is in the, I think, what I like to call the party trick category of mathematics. It's not too complicated. You can, I feel like when people are, like, when you're at a party or at a bar and things are boring, you can bring this up because people like to argue about things, and this is something to argue about. And it's nice, self-contained, look at this, it's pretty entertaining. I have a, this is a tangent, this is a, it has nothing to do with what we're doing, so sorry for the distraction. I have a tattoo on my arm that's like an Euler's equation, like the e to the I pi plus 1 equals 0. And I was at a bar once, this was like 10 years ago, and I was waiting for a drink, and a woman said, "What does your equation mean?" So I get asked that a lot, and I have my answer down to like a minute or less, like this is why it's interesting. So I answered it, and then she's like, "You should just say that it's for people who like math." So I feel like if I had launched right into the square root of 2 is irrational, maybe she would have been more entertained than my explanation for why I think the tattoo is interesting. Okay, more math. here's a few more theorems that we're not going to prove. And I include them here in the notes. Like, you read all of these, and your response is like, yeah, of course, yeah, we know, right? I get that a times 0 is equal to 0 for every integer. The negative of negative a is just a. I kind of like to just write these and just let us observe that these are not axioms. They actually can be proven from the axioms. And in a mathematical system, sort of the strength of the axioms is you see how little you need to assume and how far you can get, right? We don't need to assume that an integer times 0 is equal to 0. It can be proven. Anyway, these are theorems that you may find helpful to use. Now, let's do some mathematical induction, which feels, I think, I've heard somebody describe it. I heard someone describe it as feeling a little bit like black magic, like you almost get to prove what you want to show without and feeling like you didn't actually prove it. I don't know if I necessarily call it black magic, but it's a pretty cool trick. So with induction, it's a technique we try to use that we often find helpful if we're trying to prove something's true for all positive integers, like all infinitely many of them, or in reduced cases, like restricted cases, maybe all positive integers, but starting at 4. Maybe something isn't true until you get to like n equals 4 or something, but then it's true for everything thereafter. The problem is you can't show that something's true for all positive integers by checking it. Right? You can't check the first 1,000 or the first 1,000,000 and then say it's got to be proved. We have stronger requirements for that in mathematics. Induction is a way of sort of setting up like an infinitely long string of dominoes and then just sort of giving us the tools to like kick it off. The induction step is what sets up the dominoes, an infinite string. And then if we get the base case established, if we show that it is true for number 1, then that allows us to kind of kick off the dominoes. So the idea is, and so this first step, I call this the base case. Show that it's true when n is 1. Now, right here, this is what we call the induction step, and this is where the money is. This is where all the work is, all right? But you just assume that it's true for some integer k. You're not picking an actual integer, you're actually using k, or whatever. If you want to pick a different letter, that's fine. But you assume that it's true for some integer k and then show that it must then be true for k plus 1. If you've done that, then if it's true for 1, that induction step shows that it has to be true for 2. And if it's true for 2, that induction step shows that it has to be true for 3. And if it's true for 3, that induction step shows that it has to be true for 4. That's like the infinite long string of dominoes. That's what induction is. So we're going to do a few examples. We're going to show that the sum of the first n positive integers is n times n plus 1 over 2. So okay, we will show. The first thing I like to do is just rewrite this in the form of an equation. They say the sum of the first n positive integers, so 1 plus 2 plus 3, and then the first n positive integers plus, I don't know, n minus 1 plus n, right? We're going to show that this is equal to n times n plus 1 over 2. So we got two things to do. The first one's the fastest, the base case. If n is 1, what does the left-hand side of that equation boil down to if n is 1?
0.5.
What's that? Nope.
Oh, I mean 2 over 2, so.
Yeah, the left side, though.
Oh, I read right, so my bad.
That's okay. Hopefully they're the same. It's just 1, right? Like, if n is 1, then the left side of the equation is just one term at the end, right? The first 1 positive integers is 1, You add that single term, it's 1. So if n is equal to 1, then the whole equation (1 equals 1 times 1 plus 1 over 2, which is true. Right, 'cause somebody's already observed that that the right side does in fact give us 1. Okay, so that base case, that's the simpler step, but it's crucial. Without it, we don't get to conclude much of anything. Now this is where most of the work is. So we did the base case. Now we're going to do the induction step. And here's how the induction step generally starts. We say, suppose the equation holds for some n equal to k. So k is an arbitrary integer. I'm not actually plugging in an actual integer, but it's like a placeholder. Now that's going to get us something for free. It's going to get something that we call the induction hypothesis. Then this equation looks like 1 plus 2 plus 3 plus k equals k times k plus 1 over 2. I'm going to put a little box around this. That equation that's in our induction hypothesis, we get to use that for free. So we get that. What we're trying to show is that it's got to be true when n is k plus 1. So let's see what we get when n is k plus 1. When n is k plus 1, the left-hand side, now I'm actually writing out all in words, left-hand side, but in the future, I'm going to just call that LHS. Let's see what the left-hand side becomes. Instead of stopping my sum at plus k, I'm going to stop it at plus k plus 1. So the left-hand side will look like 1 plus 2 plus 3 plus k plus 1. I'm going to pause there for a moment. Okay. Are there questions on where we're at so far, or how we got to where we are? Okay. So we're hoping, now, before we make any more progress here, we're trying to show that this is true for n equals k plus 1, right? So I'm just going to do this up on the side. When n is k plus 1, and I often do this as side work ahead of time because it'll help me know when I've reached my goal. So when n is k plus 1, the right-hand side is k plus 1. So I'm taking this fraction here and just replacing n with k plus 1. Oops. K plus 1 is k plus 2 over 2. I put that off to the side. That's for me. So I just want to make sure I know what the right-hand side looks like so that when I'm done doing some algebra and using my induction hypothesis, if I arrive at something that looks like that, I get to say, and that's what the right-hand side is when n is k plus 1, and then we're just about done. So down here, we're going to use our induction hypothesis. And take a look at the equation we get for free up here. Right? This equation I get to use whenever I want to. And that tells me what the sum of the first k integers is. Where are we going to use that? What can we do? If only we saw the sum of the first k integers somewhere in our expression here.
Say that again. Sorry.
I said if only we saw the sum of the first k integers somewhere in that expression.
And the sum of them is a k plus 1.
Uh-huh.
Or k plus 1.
Right. So I've got the sum of the first k integers. I just have another one on the end. That's fine. But I know that that sum from 1 up to k, I can replace it with this fraction right here. So let's do it. And this is the power of induction. This is what I want us all to understand and see right now. When we make this substitution using our induction hypothesis, what we have done is we have taken this expression that has this dot, dot, dot in the middle of it. And that's the thing that's hard to work with. We can't do algebra on dot, 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 right? We have no algebraic rules there. But using the induction hypothesis, now we don't have it. We can do algebra on this now. So let's get a common denominator. Times 2 times 2. So we have k times k plus 1 plus 2 times k plus 1. Now you could distribute everything out and then unfoil, but excuse me, I think it's a little bit simpler to say, oh look, I've got a common factor of k plus 1 and just take it out. If I take out a k plus 1, what's left inside?
Plus 2.
Yeah. And I'll be damned if that isn't exactly what we said the right-hand side should be when n is equal to k plus 1. So the equation holds when n is equal to k plus 1. And now we're just going to tie things up. We've finished the induction step. Now we need to just tie things together and write a conclusion. So because the equation holds for n equals 1, and it's true for n equals k plus 1 whenever it's true for n equals k, it follows that this has to hold for all positive integers. And that's sort of like a basic bread and butter induction example. Some induction proofs are, take more work than others. But this illustrates sort of the basic mechanics of induction. You have to establish it for one particular number. You got to get your base case. And then the induction step is where all the work is, right? Show that when it's true for n equals k, got to be true for n equals k plus 1. And then their powers combined get you that it's true for all natural numbers or all integers greater than or equal to your base case.
In a formal proof that you, once you did the, k plus 1 equals, you arrived at the result k plus 1 times k plus 2 over 2 equals right-hand side, can you just say, then by induction, the final statement?
Yeah. I think so. Other questions? Okay, you want to do another one? Was that the question you were going to ask? Somebody was about to ask that. Could we do another one? Yes. Yes, we can. Okay. We're going to show that n cubed minus n is divisible by 3 for every positive integer n.
Can we actually go back? Chris?
Yes, absolutely.
I kind of missed the step when we went from, it's like our second to last equation there, the k times k plus 1.
Like going from here to here.
Yeah. What exactly did we do?
So the highlighted in blue is a common factor of k plus 1. So we took out that common factor, that's here, and then we open up a set of parentheses, and we say, what do we multiply by k plus 1 to get, this first product, and that was the k, and then what do we get it to get the second product, and that was the plus 2.
Okay.
Alternatively, you could have expanded the top and get k squared plus k plus 3k plus 2, and then unfoiled it. Yep. Okay, so let's do another one. We're going to show that n cubed minus n is divisible by 3. And another way of saying this, if it's divisible by 3, another way of saying that is to say that n cubed minus n is equal to 3 times k for some integer k. And I think that will be the helpful way of thinking of divisibility. Like if it's divisible by 3, that means it is a multiple of 3. And so thinking of it as a multiple of 3 is, I think, a helpful way to go about it. So, okay, let's do the base case. And they said for every positive integer n, that means that our base case is n equals 1. When n is 1, the expression is 1 cubed minus 1. So n cubed minus n is equal to 1 cubed minus 1, and that's 0. That's a multiple of 3. That's 3 times 0. So it's true for n equals 1. Now, the induction step. This is the fun part. We are going to suppose that this is true for some integer n equals k. What is it that we're going to show? Like, how does induction work? I suppose it's true for n equals k, then what is it up to me to show?
But it's also true for n equals k plus 1.
Right. All right. If we're supposing it's true for n equals k, that gets us something. So then that means that when n is k, this expression is k cubed minus k is 3 times some integer, and I can't use k again. I can't use k again because I'm already using it. So I'll say 3 times some integer m. So this we get for free. We can use it whenever we want. We want to show this true for n equals k plus 1, so we got to look at the left-hand side when n equals k plus 1. So k plus 1 cubed minus k plus 1. And in fact, I'm going to just expand this out, right? So k plus 1 cubed, I'm going to use Pascal's triangle to kind of help me. You could sort of do all the foiling if you want, but it'll end up being k cubed plus 3k squared plus 3k plus 1, and then I'm going to distribute that minus, so minus k minus 1. Now the plus 1 minus 1 cancels, and it is very natural to just want to combine like terms and say 3k minus k is 2k, because 3k minus k is in fact 2k, but that's not going to be the helpful way to think about this. I'm going to reorganize these terms, so I'm going to group this this minus k here. I'm going to throw it near the front. So I'm going to have k cubed minus k, and then plus 3k squared plus 3k. And I'm doing that because I want to group, I want to look at this in groups. What do I know about that, k cubed minus k? Yeah. Right, that was our induction hypothesis. That's the equation we get for free. So this is 3 times m. Now also, let's see, we have, we're bringing down plus 3k squared plus 3k. So what is it that we're hoping is true about this expression? I mean, we started here. What is it that we're hoping is true? When we say we want to show it's true for n equals k plus 1, that what's true? Say that again? Divisible by 3? Yeah, then we want to show that this is divisible by 3, and we're pretty much there, right? What's our next move? Close. Rather than divide, I'm going to factor it out. Yep. So here we have k plus 1 cubed minus k plus 1 is 3 times that expression. And then all we need to do is just make the observation, which I don't even think we have to really back it up, because m is an integer and k is an integer, so m plus k squared plus k is an integer. So cubed. And we could use the language suggested earlier. At the end, we kind of finish this part, the hard part, and we could say it follows by induction that n cubed minus n is divisible by 3 for every positive integer. How's that? Questions? Okay. Let's keep going. There's a couple of results here. First, a definition. If we have a set of integers, doesn't have to be all the integers, but some set that just consists only of integers, then we say that some integer A is the least integer of the set A, if and only if it is in the set and it's less than or equal to every other integer. Being a least integer means exactly what you think it means, in other words. The least integer of a set is unique. We will show this. We're going to suppose we're going to take a set of integers. We're going to let A be any old set of integers, and suppose that we have that it has two least elements, least integers, and then we'll show that those are in fact the same. So A and B, elements of A, are both least integers. This doesn't take too long to prove, but okay. So going up here, just by this definition, A and B are both elements of A. So if A is a least integer, because A is a least integer, and using the second part of the definition, A has to be less than or equal to B. But B is also a least integer. So what does that mean? What does that allow us to write using that same part of the definition?
B is less than or equal to A.
Mm-hmm. So if I have A less than or equal to B and B is less than or equal to A, what does that force us to conclude?
That's equal.
Yeah. So that means that the least integer is unique. Questions? Okay. So this gets us to a couple of results. One is the well-ordering principle that just says every non-empty set of positive integers contains the least element. So if you have a set that has at least a set of integers that has at least one integer in it, and it consists only of positive integers, there's got to be a smallest one, which kind of makes sense. And then the second principle of induction, or sometimes called strong induction, because we get to assume more with strong induction, is you still have to do the base case, right? So you have a statement that's true for 1, and then rather than just assuming it's true for k and showing it's true for k plus 1, what you do is say, suppose that it's true for 1 up through k minus 1, that it's true for all of them, and then it must also be true for k. We get to assume more, that's why we call it strong induction. And there are some situations where strong induction is kind of needed in order to prove a theorem. Okay, so now we're getting to the fun one. They've all been fun, I know, but we're going to go ahead and prove that there's no positive integers between 0 and 1. I like proving this because it just seems like statements that just seem obviously true are sometimes the hardest to prove. Like, what do you say other than, of course, there's no positive integers between 0 and 1. But we're going to do it, and we're going to do it by contradiction. So we're going to suppose that there's at least one positive integer between 0 and 1. So let's suppose there's at least one integer with this property. And we'll just look at the set of all of these integers. All the integers that fit this property is a set of positive integers. So I've got a set of positive integers. The well-ordering principle tells me that any set of positive integers contains a least element. So we'll call it B. So if B is in this set, right, that satisfies this, this is an integer, a positive integer between 0 and 1. Then that means I know that 0 is less than B, which is less than 1. Perfect. So now we have an inequality, a three-sided inequality. Let's multiply all three sides. Let's multiply through by B. So if I multiply all three sides, I get 0 less than B squared less than B. We're pretty close. We knew that B is less than 1, right? If B is less than 1, then B squared has to be less than 1. Which means that B squared is a positive integer. It's B squared is less than 1, and B squared is less than B. So B squared is a positive integer between 0 and 1. Which means it's an element of the set, right, that we've been talking about, and it's less than B. That's a problem for us because we said that our set has a least element and we picked it and we called it B. B was the least element in the set, so we've now reached a contradiction. And it violates the well-ordering principle. So there must not be an integer with this property. In other words, the set of all the integers that satisfy this, that has this property, has to be empty. How's that? Questions before we move on? Okay. All right, Theorem 2.4, the induction principle for integers, just says, you know, our base case doesn't have to be 1. If your base case is some other integer, then the induction technique still applies. It just, you've shown that it's true for all values greater than or equal to whatever your base case was. It's not like a whole separate technique or anything. We're going to do one more proposition. This is a fact that we used in Calc 2 when you did like infinite series. One of the things that we looked at and learned and used a lot was that, you know, we knew that exponential growth was like way faster than polynomial growth, and then, but then even faster than exponential growth is factorial growth. So if you took Calc 2, you may have spent some time wrestling with the infinite series, and that was sort of a nice fact to rely on, that factorial growth dwarfs exponential growth every time, no matter how big the base of the exponential might be. So I'm going to start here, actually just a little reminder. Does anybody know, or anybody can remind us what the factorial means?
1 times 2 times 3.
Mm-hmm. Great. Up to what?
Infinity.
No.
Up to n.
Up to n, yeah. Right, so just all the integers, multiply them from 1 up to n. That's n factorial. So we're going to show that n factorial is bigger than 2 to the n for every integer n greater than or equal to 4. It's true, like, no matter what that base is. Here we're doing it for 2 to the n. It's true for 3 to the n, and 4 to the n, and 5 to the n, and 17 to the n. What's different is for what value of n does it start being true. Right, because at first the exponential starts out bigger. The factorial will catch up, and then in fact it even grows faster and faster. So we'll just note that this is not true. n equals 1, 2, or 3. So we're going to do our base case. Our base case is n equals 4. We'll just compute n factorial and compute 2 to the 4th and see that the inequality holds. So 1 times 2 times 3 times 4 is 24. And 2 to the 4th is 16. So 4 factorial is definitely bigger than 2 to the 4th. And we're done the base case. So for the induction step, let's suppose that for some k greater than or equal to 4, that this inequality holds, that k factorial is bigger than 2 to the k. What is it that we want to show?
That k plus 1 factorial is greater than 2 to the power k plus 1.
Mm-hmm. Great. So we know our goal. So I'm going to start with something that I think will be fairly obvious. But k is greater than or equal to 4. Then k plus 1 is certainly greater than 2. Now, you could say it's got to be greater than 5. Sure. But what we need to be able to say is that it's greater than 2. We could say even more, but like that's what we need and that's what's going to work. But if we all agree that k plus 1 is greater than 2, then we're going to be well on our way. So I'm using our induction hypothesis. This is what we get for free, right? We know that k factorial is greater than 2 to the k. Now notice, this is not an equation, it's an inequality. I'm not trying to preserve equality on both sides. I just want to preserve the sense of the inequality. I'm going to perform an operation on each side. It's not going to be the same operation, okay? So that's going to feel weird, but it's going to be an operation. I'm going to do multiply by one thing on one side and one thing on the other, and we're going to be sure, we're going to be confident that we haven't flipped the inequality sign at all. So I'm going to multiply the left side by k plus 1. And I'm going to multiply the right side by 2. This is a legit move. Because k plus 1 is greater than 2. So I've taken the left side, I've multiplied it by something bigger than what I'm multiplying by on the right side. That greater than inequality, that greater than sense has to be preserved. Okay, so the right side is fairly easy because 2 to the k times 2, or 2 to the k times 2 to the first, is we add the exponents, we get 2 to the k plus 1. What should we get when we take k factorial and multiply it by k plus 1?
K plus 1 factorial.
Yeah. Right, because k factorial is 1 times 2 times 3, blah, 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 times k, and then times k plus 1. That's all the factors from 1 up to k plus 1, and that is k plus 1 factorial as desired. It follows that n factorial is bigger than 2 to the n for all n greater than or equal to 4. How's that? Okay. Questions before we? Yeah.
So the first line of the observed that part,
Mm-hmm.
and then you get to the second part, how
Mhm.
did we get there?
So on the right side, we multiplied by 2, right?
Yeah.
Which is 2 to the first. So we add the exponents.
Oh,
And that
okay.
gets us 2 to the
That
k
makes-
plus
okay,
1.
that makes more sense.
Was it? And then on the left side, every factorial contains the factorial like right below it. Like, for example, I'll do this a little side work. Like 5 factorial is 5 times 4 times 3 times 2 times 1. Well, this right here is 4 factorial. Right? So, like, you can always sort of peel off another factorial or build the next factorial. If I do 6 times 5 factorial, that's going to give me 6 factorial. Because I've got all the factors from 1 through 5, and then I add on 6, so that gives me 6 factorial. Does that answer your question?
Yeah, I guess the part that confused me was the 2 to the 1.
Oh, yeah.
I just missed that part when you said it. I assume you did.
Yeah.
So.
I don't know if I said to the 1 power. I might have just said add the
I just totally
exponents,
forgot
but
that rule
yeah.
existed.
Mm-hmm.
So,
You know, when you're learning discrete math, things have other like normal rules that we know and love and have used a million times. We like sometimes just like leave us. We're like, oh wait, you can add exponents? Like, oh yeah. Other questions?
So then how do we get to the step right after that?
So we talked about how we get from here to here. Do you have a question on how we got to this line or no?
Yeah.
Yeah. So the right side, we added the exponents, right? Because the bases are the same.
Oh, okay.
So you can add the exponents.
Okay.
Was that it? Okay. Other questions? Okay. All right, well then, we'll call it a day, and we'll talk about divisibility and primes next class. Oh, I did just, I did post assignment 4, and that'll be due when we come back. So that Monday that we get back from our break. Enjoy your day.